Okay, so this is Physics 1C for March 26th. Is this our second meeting this week? Sorry, I didn't really have anything ready for you guys last week, or last time we met. This whole setup of teaching from home is a little weird for me, so I'm doing my best. Yeah. All right, so let's start talking about electromotive force. So I've got this little picture that I pulled from the textbook. If I tried to draw this picture myself, it would be quite difficult. What this picture represents is basically a battery. Okay, so you've got what can I draw with here? Let me see something. Okay, so you've got a battery, and this represents the positive side of the battery. This represents the negative side of the battery down here. And what's happening inside of it, and it doesn't have to be a battery actually, it's called an ideal EMF source. And I guess we should define what that is. So the symbol that your textbook and most other textbooks use for EMF is this little symbol right here. So that's what we call EMF, which is short for electromotive force. And it's a word that, it's kind of an old word that is stuck around with us from previous generations when they didn't really understand what voltage was. And they knew that voltage had this effect that it pushes charges through a circuit. And so since it was pushing charges, they called it electromotive force, thinking it was a force. But in reality, it's actually a voltage, as it turns out. Nonetheless, it provides a nice analog to forces from Physics 1A. So that's why we use that phrase. So the symbol is E. Sorry about that. And this is a representation of a source of EMF. They call it an ideal EMF source. And what that means, ideal EMF source means it has zero internal resistance. Now, an EMF source, okay, I'll give you an example of some EMF sources here. Could be something like a battery. It could be a generator. A generator would be something like a gas-powered generator, maybe, would be an example of something like this. So we could say like a gas-powered generator. It's the kind of thing you can buy from Home Depot when all the power in your area goes out. I lived in Oklahoma during an ice storm where power was out to one of the major cities there for 2 weeks. And so people would go to Home Depot and they buy these generators in order to fill them with gas and, use them to power things. It could be something like, I don't know, what's another example of something that might provide a source of electricity? That's basically what an EMF source is the source of electricity. Can anyone think of anything else that provides a source of electricity? How do we generate electricity? Yeah, it could be a dam. So it could be a hydro dam. That would be another example of a generator. So it could be a gas-powered generator, but it could also be like a hydroelectric generator. Again, it's another type of generator that operates off just a slightly different principle we can talk about in a second. What other kind of sources of electricity do you guys know about? There's one that's gained, there's two that have gained like a lot more viability in the last like 10 years or so just due to improvements in technology. Yeah, solar is another one. I'll write that one. Yep, solar. And then you could also say hydroelectric. You could say slash wind here because they operate pretty similar. I'll just put up here or wind. These operate very similarly. Solar is a little bit different. Yep, nuclear would be another example too. So you could also have nuclear. All these things that I'm calling generators are very similar, and we'll talk about why. So these are all different ways that you can provide power, right? And over on this diagram right here, what we're seeing is like whatever each one of these things does, it's always going to produce a point that is at a higher electric potential. Remember, potential is voltage, okay? It's like related to energy. But whatever you do, there's going to be a point in your system that's going to be at a higher potential and a point in your system that's at a lower potential, okay? And the reality of this is that positive charges tend to collect up on the positive side right here, and negative charges tend to collect on the negative side. We'll talk about why that happens. But what that does is you have a system where you have basically this. It's kind of like a capacitor. You have a bunch of positive charges up here, right? You've got a bunch of negative charges that collect down here. This would be like, for example, in a battery, right? So you've got your battery. This is the positive side. This is the negative side. This is the inside of the battery then. Like this piece right here is the inside of the battery. And inside of here, you guys know that the electric field is going to point from positive to negative. So it points kind of down like this, right? That's the electric field within the system. What? What's up? Okay, you can see it when I do this. Can you see this, what I'm doing right now? So that's a no. And you can't see this, what I'm doing right now either, right? Okay, we'll go on to full screen then. This is going to cause you guys to have to close and reopen the stream. Or maybe I can just change settings. Nope, that's not going to work. So we'll go stop streaming. Apologize. Thank you for letting me know that. I guess I have to do full screen. That's too bad, but it is what it is. Okay, you can rejoin the stream now, and I'll give you guys a second before I start again. I'll wait to hear you guys rejoin. And tell me now if you can see what I'm doing with the mouse cursor. Great. Okay, so we have positive terminal, negative terminal. Inside, this is the electric field created. Okay, does that make sense to you guys? Just kind of like a capacitor. But the way that these things work is that when you connect something from this point up here at A around to this point right here at B, you're going to get a current, right? And I think I have a diagram of that over here too. Right here. Let's pull this one over too so we can see it. Let me make it a little bit smaller. Just put it right next to this one. So when I connect a wire, like this wire right here, into a system like this, there's going to be current that's going to flow around that, right? And even though the electric field within the battery points backwards, the electric field in the wire points this way, okay? Because the positive point right here is at a higher potential than the negative point right here, and so positive charges would tend to flow around the circuit like this. Does that make sense? So you get this electric field between these points that points this way, but between these points it's this way, okay? So what the battery is doing, okay, if it's a battery, or what the generator is doing, or what the solar thing is doing, is it's literally dragging these charges upwards due to some kind of force, and that's what we call this thing right here, the non-electrostatic force tending to move a charge to a higher potential, okay, Fn. So for each one of these objects right here, there's a different one of these. Each one of these has a different type of like non-electrostatic force, okay? So what I'm gonna do is I'm gonna say up here that we're gonna represent for all these guys what Fn is equal to, or what is the force that actually causes the charges to be pushed from the negative to the positive, if that makes any sense. Because if you think about it, think about a little positive charge that's in the circuit right here. What does it do? It goes around the circuit, it comes back to here, right? And if we want the system to actually continue to be able to provide us energy, that positive charge has to have a way to get from here back up to here, right? So it can kind of complete the circuit. Does that make sense? The non-electrostatic force is the thing that actually causes that to happen. This is the thing that actually moves the charges from the lower potential to the higher potential, okay? And what is that thing? So maybe you guys can tell me, in a battery, what is the thing, or what is the concept, or what is the energy source that provides this non-electrostatic force inside of a battery? Do you guys know? Yeah, it's like an acid-base reaction. So you could say it's some kind of chemical energy or something like that, right? It's a chemical force or a chemical energy, or however you want to say it. But that's what's providing this acid-base reaction that you're describing, right? In a solar panel, do you guys know what it is on a solar panel? I think it's easier to think about energy, by the way, than it is to think about the force, okay? But what is it in a solar panel that's providing the energy? Photovoltaic cells, but where's the energy coming from? It's pretty simple. The sun, right? So this is light energy. In particular, I mean, if we want to talk more about what's going on here in the solar panel, you know, what happens is that you've got this panel, and, right, sunlight, you know, shines down on it, and then the effect is that it literally kicks electrons off. So a little electron sitting inside here, when the light rays come in, they give enough energy to this to be kicked from the metal and be sent off like this. So that's solar. Nuclear, what does this come from? I mean, I guess it's nuclear energy, basically, right? The fact that there are certain elements that when you fire an extra neutron into their nucleus, they become unstable, right? And then they decay through a process called fission, and that process generates heat, right? So technically, what's happening here is basically something called the weak force that's freeing these particles. But at the end of the day, there's some kind of like nuclear atomic energy that's being freed. But then the thing about it is, like with this one, that this is nuclear energy. But in reality, that nuclear energy basically gets converted into thermal energy. Okay. And the same thing happens here. This is also, the gas power generator is thermal energy. You burn gas. I'll talk about how these things work here in a second. But here you burn gas, and here you basically burn nuclear fuel, effectively, to produce thermal energy. And then that thermal energy is what's used to cause the charges to move from here to here. And I'll talk about how that happens in a second. Hydroelectric and wind, these just work off of, well, hydroelectric. What kind of energy does hydroelectric use? Do I want to say, what's a hydroelectric energy generator? Like, what's an example of something like that? It's a dam, right? It's a dam. It's basically mechanical energy, or more specifically, mechanical energy we can break up into two types, right? Kinetic and potential energy, right? So mechanical, I guess that's the best way to say it. You use the gravitational potential energy of falling water so that it gains kinetic energy and then rolls itself over turbines, and those turbines, the motion of the turbines creates an EMF, and we'll talk about why that happens, but we need to talk about magnets before we can do that, okay? So this one, as you said, I think mechanical energy is definitely the best way to say it, and then would you guys agree that wind is the same thing? Right, because wind is just that, right? Do you guys want to talk about, in general, like how these things actually work at all? Are you guys curious at all, like how does a generator work? Okay, so this is how a generator works. Let's look at the simplest version. So let's look at a like any kind of like gas powered generator. Okay, so the way it works is this. This is gonna be very crude drawing here. Let's use like brown, like bronze, whatever. So we've got some wood, let's say. Okay, we're gonna start a fire with this wood down here. So we've got some wood, and we light it on fire. Okay, so we've got a little, whoops. So we've got a little fire right here. This looks like children's drawing, but whatever. And then we take like a pot of some kind. Okay, so we've got, we'll just make a really large vessel right here. And it's gonna be kind of like a steam kettle, all right? And we're gonna fill it with water. So inside of here, can I get a thicker pen? There we go. So inside of here we have water. You may have talked about this if you took 1B, by the way, I don't know. We've got water in here, right? The water has the effect of, you know, boiling when it's placed near water, right? And then that has the effect of causing these little steam droplets to like spray out here, right? So you got this stream of steam coming out here, right? And as that steam comes out, it starts to dissipate out, right? And expand because it's coming out of this nozzle. Now all you need, in order to harvest the energy, is you need to take the speed at which this steam comes out, and you need to convert it into mechanical energy, okay? And the way you do that is with a turbine. So right here, you have some kind of a turbine that's able to spin about some axis right here. And the motion of this causes the turbine to turn around like this, okay? And the moment that you have this type of motion right here, and this is the part where I'm gonna gloss over some details. Once you have this type of rotational motion, you can automatically turn that into energy. Now, you can understand this in a really simple way if you think about, like, historically, the way that people produced energy, like in, let's say, the 1200s through the 1500s, would have been by putting, like, a water wheel near a river, right? And you can use that water wheel and the motion of the water wheel to, like, grind stone or to grind flour or something like that from wheat. Or, like, a windmill that would rotate around, you could use that windmill's motion to do work for you, right? The idea is that as long as you can get something to move like this, you now have energy that you can harvest, right? Specifically, the way we harvest this, though, is we add a magnet, so that motion plus a magnet leads to EMF. And we will talk about this process. This is the black box that we'll talk about later that's due to a phenomenon that's known as Faraday's law. So we'll talk about this here in a couple weeks. Describes exactly how you take a motion of a magnet and you produce an EMF, okay? But the key thing is just the moment you have this kind of motion, you automatically produce electricity, basically. EMF is basically just electricity, right? So this is what you need. You just need something that's hot, right? You need anything that's hot. The hot thing could be, you know, it could be fuel, right? It could be like specifically what we normally use, which are fossil fuels. Or it could be nuclear fuel. Or it could be geothermal. This is where you use the fact that there are certain places on the Earth that are closer, like the crust is thinner, and so the mantle is closer to the surface, and so you have like hot, right? You just need heat, basically. If you can get heat, then you can do this, and you add a magnet, you get electricity. This is how we produce all electricity in the entire world. It's produced by this process, primarily, other than one exception, I think just one exception, which is solar. This is the one that has this one right here is the big exception. Solar is a completely different process. It's also one of the best processes we have because it doesn't pollute. The problem is it's not very efficient. These ones, nuclear and gas. Gas could mean coal. It could mean gasoline. It could mean natural gas. It could mean any number of things that we burn. It could also be like biofuel. It could be like burning corn or burning wood as well. Any of those things can be used to make this process happen. All right, does that all make sense to you guys? Do you guys have any questions? I'm gonna get some water. Why don't you guys think if you have any questions and let me know. Be right back. Okay. I'm back, but I can't hear you guys yet. One second. Okay. So, did anyone have any questions? Nothing? All right. I hope you guys start talking eventually. Otherwise, it's just me talking to myself here. Okay, so this is EMF. The idea that this thing, a battery, a gas power generator, etc., any of these objects can produce this non-electrostatic force, which has the tendency to move charges to a higher potential. And that is what allows an electrical circuit to continually produce energy, or at least to continually deliver energy to whatever's going on in the circuit. Does that all make sense to you guys? All right. So the next thing I want to mention is just like how you can try to relate what this battery is doing to something that you might understand. So this is kind of an analogy that I like to use. It's a pretty common analogy, I think, that's used for an electrical circuit and a battery and stuff like that. So this isn't perfect, but it works pretty well. So let's say we take a circuit, okay? And our circuit is going to contain just a really simple system. You're going to have an EMF source. So now we're going to start labeling. When we have batteries now, we're usually going to put this little symbol E. You'll see this on your homework a lot. And we're going to connect this up to a circuit. So our circuit's going to go like this, and I'm going to add into the circuit a resistor. If you guys remember, the symbol for a resistor looks something like this. And then we're going to connect these back around here. So here's our circuit. And then around this circuit, I'm going to draw like the analogy for what it's doing. So the analogy for what's going on here would be something like this. So imagine that we have a tube, okay? And our tube, we'll use a thick pen for this. Our tube is basically going to do something like this. So it goes up this way, it goes along this way, and then it goes to here, and then the tube opens up. And at the bottom down here, I really should use different color for the water, I guess. Probably should have done. So at the bottom down here, we have water filling up this system. You know what? This is going to look better if I like draw tubes. So let's do here. Black. Okay. So we have a, ooh, not like that. No. So imagine you've got a tube that goes around like this, and then it opens up right here. So there's an opening here. And this tube has a vessel down here that's now filled with water. So there's a reservoir of water down here that you can draw from. And this water, it is going to be allowed to flow through your system via a pump. So right here in the middle of my system right here, I'm going to erase this and say, suppose that we have some kind of a electrical or something pump that we put in here. So we throw in here a pump. So some kind of a pump right here. And the pump and the EMF are basically going to be analogs to each other. So the pump, what it does is when we turn it on, it allows the water to flow through the system, right? So water now is going to flow basically up in this direction. So the water is going to flow up this way. It flows up to here. And then once it gets to this point, it's gained gravitational energy, right? So now it can flow this way, and then it can come over here, and it can basically drip out this thing right here, right? And so you have water drops that are coming down this way. And maybe you even have like a stream of water that's flowing this way, right? So the EMF source is like the pump, okay? The pump has the effect of raising water from low potential energy to high potential energy in terms of gravity, right? Does that make sense? That's what the pump does, right? It takes the water, it drags it up to a higher potential energy. And then using that potential energy, gravitational energy, it gains kinetic energy, which can then cause it to push along the circuit here, or the tube, and then flow out this direction, okay? What the EMF source does is it does exactly the same thing, except that instead of water, what you have are charges. It takes charges from the low potential side of the battery, so this side right here, right? That's the low potential, the low V, and this is the high V. And then once you have a charge right here, it naturally is going to want to go and fall back to this point right here. So that's the motion of the charges in the circuit, right? Like that's the current flow. We call that current I, right? And the charges tend to flow around the circuit, and they just kind of keep going like this. They dissipate their energy once they get to this thing right here. This is what we call a resistor. And the effect is of the resistor, if we remember from last time, is the resistor has the effect of converting the electrical energy into thermal energy. So this thing kind of starts to heat up. And the resistor could be anything like, you know, it could be something like a light bulb, for example, right? That resistor could be a light bulb, and it could light up, right? So can anyone tell me, what would be an analog to something? So this resistor, it basically, it uses the energy of the battery, right? Oh, whoops. It uses the energy of the battery, right? Does that analog make sense to you guys? That analogy make sense to you guys? So what would be an analog to the resistor then? Can you guys think of anything that would be an analog to the resistor? What could I add into my system, let's say right here, where we have the energy of the flowing water? How can I extract that energy? Any ideas? Well, the sponge would absorb the water. Yes. Could I then use that to do any kind of work, though? A wheel, right. So you could just throw a wheel in here, right? Like a water wheel. And then you turned the falling water, right? This is basically what a hydro dam does. You throw... I hate how I have to... Yeah, if you throw a little turbine in here, a little water wheel, then the flowing of the water is going to cause that water wheel to turn around in a circle, right? It's going to keep moving. And then you can use that motion to do whatever you want to. You can use it to power something or grind wheat or whatever you want to do, basically. But that's basically what an electrical circuit is. It is a much simpler way of doing what I just described with the water, right? Because if you think about the way water works, let's say that this reservoir we have down right here, that water is eventually maybe going to evaporate, right? Or you may have some problems that within the system, because you have water flowing all the time, you have a lot of, like, I don't know, oxidation or rust occurring inside of the tubes, and then maybe you need to replace the tubes and stuff like that, right? Electricity is way more efficient because when we connect these systems up like this, while you do have some kind of like long-term effects that the circuit will over time not be as good and you'll build up some resistance in the battery and stuff like that, you can replace the battery And the wires themselves tend to basically keep working for a very, very long time. You know what I mean? And you don't have the messiness or the size of what this whole system with the water does, right? You don't need water to refill it or anything like that. It's a circuit. And that's what electricity is, right? It's this thing that we use to do work for us, right? And it's one of the most efficient ways that we can use to convert a source of energy into meaningful work. And we can use it to power light bulbs and TVs and all the other things that we do. But at the end of the day, it's just something that does work for us. And it all starts off with what we began with here, which is this thing, the EMF source. The EMF source, that's the key thing, is the EMF source. You have a battery, a generator of some kind, whatever you've got. But when we use the word EMF, that's what we're saying. We're saying you have some source of energy, effectively, or an electromotive force that tends to push the charges from down here up to there. That's what the EMF is the force that causes the charges to migrate from the negative to the positive against the electric field, and that's what this picture right here represents. Okay, so that's a bunch of theory. Do you guys have any questions? I think that's a no. Okay, I'm going to stop.